Messy code. JavaScript enables us to make websites or web apps dynamic. Unfortunately, most JavaScript code is written using an architecture that could be best described as messy. So what warrants messy code, and why should it alarm us? Single file. Using a single file to store all of our JavaScript makes it very difficult for us to locate functions. Not only does this increase development time, but it also increases the chances of duplicating method functionality. By simply grouping small, single responsibility functions into separate files greatly facilitates code reuse and enables faster development. Global scope. If only small, separate files were all that was required to unclutter our code, the biggest issue in most JavaScript is scope, and in particular global scope. We will explore scope in greater detail in the next section, but first we will explore why we require a solution. Due to the existence of global scope, even if we split our larger file into small separate files, each function can still be accessed from all other functions. This is a really negative architecture, as it does not force developers to use the correct function for the required solution. And once your code starts permitting any function to access any other function, the result is a deeply coupled code base, which is difficult or impossible to update and maintain. JavaScript scope. In its simplest terms, a scope is an encapsulated section of code. As can be seen, the function scope1 declares its own scope, and so does scope2. Both functions declare their own versions of the variable a without affecting each other. These functions sit inside the global scope, where it too declares a value for the variable a. If we now add a new function, scope3, we can see this new function outputs the value 4, even though it doesn't actually declare the variable a. This is because when an object is requested within a scope, the compiler searches up the parent scope chain looking for its definition. In this case, it finds the definition of a in the global scope. We can clearly see this object searching within the parent scope chain here. As can be seen, the function scope3 requires the variable a. It doesn't have a declaration itself and so searches its parent scope, the function scope2. This function also doesn't have a declaration for the variable, and so the search continues into the function scope1, where the compiler finally identifies the declaration of the variable a. Scope isn't just declared using functions. Loops and if statements also declare their own scope. As a general rule, the use of curly brackets indicates the boundaries of a new scope. Scope can also be used to hide functions. Here, the function scope3 cannot be seen from the function scope1. It is effectively hidden. JavaScript closures. Closures happen as a result of writing scoped code. You don't intentionally have to create a closure, although you have been writing them without realizing it. Closures are all around you in JavaScript. You just have to recognize and embrace them. If we examine this code, when the doCalculate function is called with a parameter 4, the result of 24 is output. This is the result of the multiplication of 2 times 3 times 4. The function calculate has access to the inner scope of initialize, which permits it to access the variables a and b. But because of scope, the function calculate can only be accessed from within the initialize function. To permit access to the calculate function from outside the scope of initialize, the calculate function is returned from initialize. After we execute initialize, the function calculate is returned and assigned to the variable doCalculate. The calculate function is now outside the scope of the initialize function, but it still has access to the variable b, which is within the scope of the function initialize. This is a clear observation of closure. A more obvious example of closure can be seen from this code. As we execute the code, we can see that the number 6 is output 5 times. Not quite what we expected. What we wanted to occur was the numbers 1 to 5 to be outputted. But why didn't this occur? The reason is because the for loop increases the value of I until it reaches the value of 6. Because the timer does not call until 1 second later, the for loop has already ended and the value of I is 6, which is why the timer repeatedly outputs the value of 6 5 times. But how do we correct the code so that it correctly outputs the values 1 to 5? There are 2 possible solutions. The first involves inserting a new scope between the loop and the timer. This is done by utilising a self-executing anonymous function, which preserves the value of I into the new variable j. Because this anonymous function creates its own scope, then when the timer requests the value for j, it is correctly the incremented values 1 to 5. Alternatively, the let keyword could be used. Whereas the var keyword is scoped to the nearest function, the let keyword is scoped to the nearest enclosing block, which in this case is the for loop, which means that a new instance of j is created for each iteration of the loop, thus preserving the value of I into j so that the values 1 to 5 can be outputted correctly. The factory pattern. As can be seen from our exploration into scope and closure, it is not only possible to hide functions away inside other functions, it is also possible to export out inner functions. This is the basis of the factory design pattern. As can be seen here, the function getA sits within the object innerObj, which itself is hidden within the function factory. Normally, this would mean that the function getA would be inaccessible from outside the factory function scope. But in this example, it is accessible. Why? The reason is because the factory function's main objective is to create a new accessible method. It does this by defining the object innerObj, which encapsulates the function getA, and then returns it. So effectively, the variable factory actually equals the object innerObj, which is why it is now possible to access the function getA. As can be seen here, the factory function must first be executed before any function access is permitted. This is because until the factory is executed, innerObj is not defined or returned, so the factory variable is actually undefined. The problem with this technique of creating a factory function is that the initialization process must only ever be done once, so this line of code would only work the first time it was called. A more accurate solution is to use a self-executing anonymous function. As can be seen here now, the factory function is initialized as soon as it's assigned. The injection pattern. Although the factory pattern solves many of the clean coding issues we identified earlier, it still has the issue of how do factories utilize each other. As can be seen here, the function factory B requires access to the getA method from the function factory A. It does this by using the global scope. But there must be a cleaner method without touching global scope. This can be done using the injection pattern. The objective of this pattern is to ensure that any other functions that a particular function may require access to are injected during the initialization process to prevent the need to access the global scope. But there is still a slight issue with this solution. The entire factory A function is injected into factory B, even though it only requires the function getA. So a much cleaner and safer solution would be to just inject the getA function. The module pattern. When used together, the factory and injection patterns produce the module pattern, which greatly facilitates clean coding. But it doesn't exist with the global scope congestion. This issue still exists because when these modules sit in different files, they require a way of communicating with each other. Even using the module pattern where each individual file has just one global scope variable, over a whole project, this escalates beyond what is acceptable. Is there a way of linking separate files by just using one global scope variable? Yes, this could be achieved using a module manager, as shown here. The module manager is assigned to the global scope variable $cm and has two methods, addModule and getModule. Using this manager, it is possible to store modules in separate files using just the single scope variable. These modules can now easily be recalled as well. Summary. Hopefully it can be seen from this small video that by using a few simple design patterns, it is possible to create clean JavaScript.